and specifically solving non-smooth, non-convex optimization problems. So it's collaborations with groups from both optimization and geometric integration communities. So just first to give a bit of context for using tools from numerical integration for optimization problems. So basic notions of optimization is if you want to minimize the function v, you have the gradient flow system of differential equations, and the sort of main building blocks of optimization methods that are first order, which is explicit gradient descent and proximal mappings, comes from applying forward Euler and backward Euler discretizations, respectively. And more generally, tools for solving differential equations, so numerical integration. In recent years, there have been loads of applications for understanding sort of frameworks of optimization for devising new optimization schemes. So a prominent one has been to understand acceleration phenomena, so relating Nesterov acceleration to some second-order ODEs, and understanding how methods from symplectic integration can be used to preserve this acceleration phenomena in discrete time. People have also looked at sort of taking other systems that have some dissipative structure and apply them in the context of optimization. Right. But what we're interested in is geometric numerical integration. So this is the subfield where you're interested in geometric structures of your differential equations. So these might be some conservation laws, symplectic structures, or even an energy dissipation law. And you're interested in discretizing the differential equations while preserving this structure. Discrete gradient methods are a group of discretization techniques that are designed to preserve several structures. So they preserve first integrals, meaning energy conservation laws and dissipation laws, and they also preserve the Lyapunov functions of systems. And often these are used to achieve long-term stability of your numerical scheme. So you can see sort of the difference of not using discrete gradients to using discrete gradients and achieving long-term stability of your simulations. But in the context of optimization, you're more interested in preserving the behaviors of dissipation of your system. So just to briefly define what the discrete gradient is. So given a smooth function f, a discrete gradient is any mapping that takes two vectors x and y as input and satisfies two rules. So it has to converge to the gradient when y converges to x. So it's consistent with the actual gradient. And for any two vectors y and x, it has to satisfy this mean value property, that the inner product of the discrete gradient with the difference of the two vectors is equal to the function difference. Well, the function value difference. And essentially this mean value property allows you to prove all the structure preserving properties of the discretization methods. So if we look at just regular gradient flows, this has a dissipative structure you can derive by applying the chain rule, and you can get the sort of discrete analog of this dissipative structure just by applying the mean value property of discrete gradients when you've discretized gradient flow. So that's sort of the starting point of the discrete gradient method. Just briefly to mention some examples of discrete gradients, because there are basically arbitrarily many types of discrete gradients. Two common ones that both involve computing gradients of the function is the Gonzalez midpoint discrete gradient and the mean value discrete gradient. But a third one, which is more of interest to us, is the e to abe, or coordinate increment discrete gradient. So this one is derivative free, and it's evaluated between two vectors x and y by computing successive difference quotients, updating each coordinate as you move along. And so people have looked at applying the e to abe discrete gradient to gradient flow and used this as an optimization method. So this has previously been applied in the context of image in-painting to solve variation problems with Euler's Elástica regularization. And the motivation for this was that the gradient can be quite expensive to compute, so something that's derivative-free might be competitive with gradient-based methods, and they got nice results competitive with state-of-art methods, and the discrete gradient methods handled non-convexity quite well, didn't get stuck in local minima too much. Also, if you apply the eta discrete gradient method to a least squares formulation for a linear system, then you end up with classical methods like successive over-relaxation and the Gauss-Seidel method. And people also looked at applying these on Riemannian manifolds. So just to sort of emphasize a bit more the derivative-free structure of applying the eta discrete gradient method, we can rewrite this scheme accordingly. So first we fix a direction dk that could, for example, cycle through the standard coordinates. Then along each coordinate, you solve a scalar nonlinear system of this form. And this is quite computationally tractable. You can do it in a few time steps. You can do it in a few function evaluations. And then you have this dissipative structure that sort of generalizes gradient flow dissipation, but it's derivative-free, so your updates dissipate like this. And this is well defined for non-smooth functions. It's also computationally tractable, so you can still implement this in a non-smooth derivative-free setting. And you can also quite naturally generalize this, going from cycling through the standard coordinates to choosing randomized directions on any unit sphere, for example, or randomizing the choice of standard coordinates. Right, so I'll talk about how we want to apply this in non-smooth, non-convex optimization. So the motivation for looking at this method in this setting is basically for solving problems that are non-smooth and non-convex and where we can't easily compute gradients. So one typical example is bi-level optimization of variational regularization problems. So if you want to optimize the parameters that go into a variational regularization model, for example, weighting your regularization terms or something else, these can be quite difficult to compute gradients for, especially if your variation problem is non-smooth. Other parameter optimization problems that you can't easily compute gradients for, this is quite broad. One example being optimizing the placement of cameras for observing robotic behavior. And other motivations which were also used, for example, for Euler's elastic painting, is when gradients are computationally expensive, or when your problem is poorly conditioned or stiff. So the final example here, the motivation of using discrete gradient methods for this is that your dissipative structure holds for any time step, so you have sort of unconditional stability. So you're not restricted with regards to your time steps. Right, so in order to prove anything about this method in a non-smooth, non-convex setting, we need a notion of stationarity for non-smooth, non-convex functions. And for this we have the Clark subdifferential, which is a quite good framework introduced by Clark in '73. So essentially, if you have a function that's locally Lipschitz continuous, then you can characterize its sort of first-order behavior as a subdifferential, which is the set of essentially the convex hull of all limit sequences of gradients in a neighborhood. Because you know that if a function is locally Lipschitz continuous, then it's almost everywhere differentiable. So if you just look at all gradients in an immediate neighborhood at a point x, then you get a notion of a subdifferential. So if you're familiar with subdifferentials for convex functions, this definition coincides with that whenever your function is convex. And it has nice analytical properties for local Lipschitz continuous functions. So it's a set value mapping that's outer semi-continuous. It has a mean value theorem, and the sets are convex, compact, and non-empty. So this makes it quite good for sort of dealing with theoretical questions. And we say that a point x is a Clark stationary point of f if 0 belongs to the subdifferential. So this sort of generalizes a first-order criteria for smooth functions. And another way of looking at stationarity for local Lipschitz continuous functions is that this Clark directional derivative is non-negative for all directions on a unit sphere. So that's an equivalent condition. So unlike smooth functions, where it's enough to check stationarity along the standard coordinates, for non-smooth functions you actually have to ensure that it's stationary along all directions on the unit sphere, which means that we also need to change how we implement the e-to-ab method. So we'd like to basically run the e-to-ab discrete gradient method and ensure that all limit points of the iterates will be Clark stationary. And to go about proving this, we can use the outer semi-continuity of the Clark subdifferential, which is related to the upper semi-continuity of the directional derivative. We know from basic discrete gradient method properties that these two expressions converge to 0 as the iterates go to infinity. And since we also have upper semi-continuity of the directional derivative, then we know that in the limit it will have a non-negative directional derivatives, provided that all sort of subsequences of our search sequence dk are dense in some sense. And so we can do this both in a randomized setting, so when we choose random directions dk on the unit sphere, or when we choose deterministic directions on the unit sphere. So the criteria is just that you sample with a full support on the unit sphere, or that you have something we call cyclical density. And this enables us to prove that all iterates of these methods will converge to a connected compact set of accumulation points. All the accumulation points take the same value, and they're all Clark stationary. So we know that this method does work well, even in a black box non-smooth setting. And we can also adapt this to solve problems with constraints, even if the constraints are non-smooth and non-convex. And another benefit of, so we apply them to different parameter optimization problems. So here we're optimizing the two parameters for second order total generalized variation denoising, basically. Another benefit with this perspective of geometric integration is that even though it's a sort of black box method, if the underlying function has better properties, like if it has Lipschitz continuous gradients and convex, then the method inherits the normal rates from gradient descent. So you get 1 over k rate for convex functions. It gets linear convergence rates for strongly convex functions and Polyak-Jovashevitz functions. You get slightly better convergence rate than explicit coordinate descent. The complexity of the method grows only with dimension n as n. So in the setting of sort of non-smooth optimization, it has better complexity than many other methods. You can sort of use Kudyka-Jovashevitz inequality analysis for smooth functions to show that it has a finite path, so a unique convergence point. And all of these properties that I talked about also hold for our arbitrary choices of time steps. So all of this unconditional stability feeds into this as well. So I'll just briefly finish by mentioning that you can also apply discrete gradient methods to other dissipative systems. So we looked at inverse scale space flow, which is sort of the corresponding continuous time flow for Bregman iterations. So we can use this to promote, for example, sparsity of your solutions. So this also is implementable in a derivative-free setting and for non-smooth, non-convex functions. We can, for example, do this to promote sparsity. So going back to just linear systems and least squares formulations. So the normal e-to-ab method corresponds to Gauss-Seidel methods, basically. And that's the blue plot. And then if we know that the ground truth is sparse, and we promote some sparsity through an L1 norm in this function that defines basically our inverse scale space flow, then we improve the convergence rate of the scheme significantly. And we also can, for example, detect the support to much higher accuracy of the signal. So you can also sort of take these methods beyond gradient, the standard Euclidean gradient flow. that's it. Thanks for your attention. Well, they're implicit, so you're always solving some nonlinear step at each scalar update. So if you're in a black box setting where there's some significant cost to each function evaluation, and you can compute gradients, then you definitely want to do that. I mean, you could definitely devise, you can obviously devise problems that it'll struggle with, and you might then also have certain derivative-free methods that handle that better. But I don't know which ones, and I think like most sort of features that this will struggle with, most of the other derivative-free solvers will also struggle with. And this one does handle non-smooth functions a lot better than derivative-free methods that don't take into account the non-smoothness, for example.
Okay, well, thank you again.